Picture this, a silent, endless expanse where stars flicker like distant candles, galaxies swirl in slow motion, and darkness stretches farther than the mind can grasp. Somewhere in that infinite blackness, hidden among the glittering tapestry of the cosmos, lurks one of the universe's most enigmatic forces, the black hole. Not just a void, not just a shadow, but a cosmic sculptor, shaping the very fabric of galaxies with its unseen hand. Tonight, let your mind wander into the depths of space, where gravity bends light, time slows to a crawl, and the fate of entire galaxies is written in the silent dance of these mysterious giants. Close your eyes, breathe deeply, and let the universe carry you away as we uncover the hidden role black holes play in the story of everything. Where are you joining us from tonight, and what does the sky look like above you? Let's drift into the stars together. Now, let's journey to the very beginning, the moment a black hole is born. Imagine a star, not just any star, but one so massive it dwarfs our own sun by many times. For millions of years, this star burns bright, fusing elements in its core, fighting against the crushing weight of its own gravity. But eventually, even the mightiest stars run out of fuel. When that happens, the balance tips, gravity wins. In a cataclysmic explosion known as a supernova, the star's outer layers are blasted into space, while its core collapses inward with unimaginable force. If the core is massive enough, nothing can stop its fall, not even the laws of physics as we know them. It shrinks denser and denser until it becomes a singularity, a point where gravity is so strong that not even light can escape. This is the birth of a stellar mass black hole, but not all black holes start this way. At the centers of galaxies, something even more mysterious lurks. Supermassive black holes, weighing millions or even billions of times more than our sun. How these giants form is still a puzzle, but one theory suggests they grow from smaller black holes, merging and devouring gas and stars over billions of years. Another possibility is that they were born from colossal clouds of gas, collapsing directly into black holes in the early universe. Whatever their origin, their presence is undeniable, their gravity shaping entire galaxies around them. Now, picture standing near one of these cosmic monsters. Not too close, of course, because once you cross the event horizon, the boundary where escape becomes impossible. There's no turning back. Space and time twist in ways that defy intuition. The pull of gravity is so intense that it stretches anything nearby into long, thin strands, a process called spaghettification. Even time itself slows down near a black hole, warped by the sheer force of gravity. It's a place where the universe's rules bend to their breaking point, a reminder of just how strange and awe-inspiring the cosmos truly is. And yet, these terrifying giants are also architects. Their immense gravity herds stars into orbits, stirs up cosmic storms, and even sparks new star formation in distant corners of galaxies. They are destroyers and creators, shaping the universe in ways we're only beginning to understand. So as you drift deeper into sleep tonight, imagine the quiet power of a black hole, the silent force that bends the very fabric of space, guiding the dance of galaxies across the endless night. Now, let's turn our attention to the different kinds of black holes that exist in the universe. Just as stars come in various sizes and forms, so do these cosmic enigmas. The smallest among them are stellar mass black holes, the ones born from the dramatic collapse of massive stars we just explored. These typically weigh between 5 to 100 times the mass of our Sun. Though small in cosmic terms, their gravity is still unimaginably strong, capable of pulling in nearby gas, dust, and even other stars. You'll often find them scattered throughout galaxies, lurking in the darkness where once great stars met their end. Then there's a middle ground, intermediate mass black holes. These are the cosmic missing link, with masses ranging from 100 to 100,000 times that of our Sun. Scientists are still piecing together how they form. Some theories suggest they grow from mergers of smaller black holes, while others propose they arise from the direct collapse of massive gas clouds. They are rarer and harder to spot, but recent discoveries hint that they might dwell in dense star clusters or the hearts of smaller galaxies. But the true giants of the black hole family are the supermassive ones. These colossal beasts, weighing millions or even billions of solar masses, sit at the centers of nearly every large galaxy, including our own Milky Way. Unlike their smaller cousins, their origins remain one of astronomy's biggest mysteries. Did they grow from smaller black holes, merging over eons, or were they born already massive in the chaotic early universe? What we do know is that their influence is unmatched. Their gravity shapes entire galaxies, dictating the motion of stars and gas on scales we can barely comprehend. So whether small, medium, or unimaginably large, black holes come in many forms, each playing a unique role in the cosmic story. And as we continue our journey, we'll see just how these mysterious objects shape the galaxies they call home. Now, let's take a closer look at where these supermassive black holes tend to make their home right at the very center of galaxies. Picture a bustling city with a towering skyscraper at its heart. In much the same way, nearly every large galaxy we've observed has a supermassive black hole anchoring its core, acting as a gravitational focal point for everything around it. Our own Milky Way is no exception. At its center lies Sagittarius, a star, a supermassive black hole with a mass roughly 4 million times that of our Sun. For decades, astronomers suspected something massive was lurking there, but it wasn't until recent advancements in technology that they could confirm its existence. By tracking the orbits of stars near the galactic center, scientists observed them whipping around at incredible speeds, a telltale sign of an invisible but immensely powerful object pulling the strings. Beyond our galaxy, the evidence is even more striking. Take the nearby Andromeda galaxy, for example. Its central black hole is even larger than ours, weighing in at a staggering 100 million solar masses. Then there are the active galaxies, where supermassive black holes are surrounded by glowing disks of superheated gas, shining brighter than all the stars in their host galaxies combined. These luminous beacons, known as quasars when seen from across the universe, are some of the most energetic objects in existence, and they all trace back to the same thing, a ravenous black hole at the center. But how do we know these aren't just theoretical ideas? The proof comes from multiple lines of evidence. Radio telescopes have mapped the intense emissions coming from galactic cores, while X-ray observatories have detected the high-energy radiation produced as matter spirals into these cosmic pits. Even gravitational wave detectors have picked up the ripples in space-time caused by black holes merging, further cementing their reality. So whether quietly lurking like Sagittarius, a star, or blazing brightly as a quasar, supermassive black holes are the silent architects of their galaxies, shaping their structure and evolution in ways we're only beginning to understand. And as we'll see next, their influence extends far beyond just sitting at the center. They actively shape the destiny of everything around them. Now, let's explore the invisible hand guiding the dance of stars and gas around these cosmic giants. Black holes don't just sit quietly at the center of galaxies. They actively shape the motion of everything nearby with their immense gravitational pull. Imagine a whirlpool in the ocean, dragging nearby objects into its swirling currents. In a similar way, black holes warp the fabric of space itself, bending the paths of stars and gas clouds as they orbit. Some stars get caught in tight, fast-moving orbits, whipping around the black hole at speeds that defy imagination. Others, like gas clouds, spiral inward, heating up as they go and creating brilliant displays of light. But this gravitational influence isn't always orderly. Sometimes, stars stray too close and are torn apart in violent events called tidal disruption flares, sending shockwaves of energy through the galaxy. Even more fascinating is how black holes can fling stars away entirely. When a star gets too close to a black hole but isn't fully consumed, it can be hurled outward at incredible speeds, becoming what astronomers call a hypervelocity star. These rogue stars race through the galaxy, sometimes even escaping it entirely, all because of a single gravitational encounter with a black hole. Gas clouds, too, face dramatic fates. Some are pulled into swirling disks around the black hole, fueling its growth and lighting up the galactic center. Others are ejected in powerful outflows, pushed away by the intense radiation and magnetic fields generated near the event horizon. This push and pull creates a dynamic, ever-changing environment where chaos and order exist side by side. So while black holes may be invisible, their influence is anything but. They sculpt the movement of matter on a grand scale, turning the centers of galaxies into cosmic laboratories where gravity reigns supreme. And as we'll see next, this gravitational dominance doesn't stop at mere motion. It fuels some of the most energetic phenomena in the universe. But the gravitational pull of a black hole doesn't just distort orbits. It also creates some of the most spectacular light shows in the universe. When gas and dust spiral toward a black hole, they don't fall straight in. Instead, they form a swirling, superheated disk called an accretion disk, spinning at nearly the speed of light. Picture water circling a drain, but on a cosmic scale, with temperatures reaching millions of degrees. This incredible heat causes the disk to glow intensely, often outshining entire galaxies. Within this chaotic environment, something even more extraordinary happens. The black hole's powerful magnetic fields and rapid rotation can launch narrow beams of particles outward at nearly light speed. These are cosmic jets, stretching thousands of light years into space. Think of them as cosmic fire hoses, blasting energy and matter far beyond the black hole's immediate reach. These jets can plow through surrounding gas clouds, heating them up or even pushing them out of the galaxy entirely. The impact of these jets is staggering. Where they collide with interstellar material, they create shockwaves that trigger new star formation, or, in some cases, halt it entirely by scattering the very gas clouds that stars are born from. It's a cosmic tug of war, where black holes can both give life to new stars and snuff out the conditions needed to create them. And here's the twist: these jets aren't just destructive. They act as galactic feedback mechanisms, regulating how much gas remains in a galaxy over time. Too much activity, and the black hole can starve its own galaxy of fuel for future stars. Too little, and gas might accumulate unchecked, leading to runaway star formation. It's a delicate balance, one that shapes the evolution of galaxies across billions of years. Next, we'll see how this balancing act turns black holes into something far more than cosmic vacuum cleaners. They become the engines that drive entire galaxies. Now, let's take a closer look at how black holes transform from cosmic destroyers into something far more surprising: galactic engines. Imagine a black hole not just as a devourer of stars, but as the powerhouse behind an entire galaxy's growth and structure. These cosmic giants don't just sit quietly at the center of galaxies, they actively shape their surroundings, influencing everything from star formation to the movement of matter across unimaginable distances. One of the most fascinating ways black holes act as engines is through their ability to redistribute energy. When a black hole feeds, it doesn't just consume material, it releases enormous amounts of energy back into its galaxy. This energy can heat up surrounding gas, preventing it from cooling and collapsing into new stars. In some cases, this means putting the brakes on star formation, effectively controlling how quickly a galaxy grows. But in others, the shock waves from jets and outflows can compress nearby gas clouds, triggering bursts of new star birth. It's like a cosmic thermostat, regulating the galaxy's activity over billions of years. But the influence of black holes doesn't stop there. Their gravitational pull can also sculpt the very shape of a galaxy. Supermassive black holes, with their immense gravity, tug on stars and gas, creating intricate patterns of motion. In spiral galaxies, this can help maintain those beautiful, swirling arms. In elliptical galaxies, black hole activity can stir up the orbits of stars, smoothing them into their characteristic rounded shapes. Without these engines at the core, many galaxies might look and behave very differently. And here's something even more mind-blowing: black holes may help distribute heavy elements throughout the cosmos. When they fling material outward in jets and winds, they carry elements like carbon, oxygen, and iron, ingredients essential for planets and life, far beyond their home galaxies. This means black holes don't just shape galaxies, they might also see the universe with the building blocks of future solar systems. So the next time you picture a black hole, don't just think of it as a cosmic vacuum. Think of it as the engine room of a galaxy, driving its evolution in ways we're only beginning to understand. Up next, we'll explore how these engines can both ignite and extinguish star formation, revealing the delicate balance that keeps galaxies alive. Now, let's uncover the fascinating duality of black holes, how they can play both the role of cosmic sculptor and cosmic saboteur when it comes to star formation. Picture a galaxy as a vast nursery where stars are born from clouds of gas and dust. Black holes, sitting at the center, hold the power to either nurture or disrupt this process, depending on their mood. When a black hole is active, feeding on surrounding material, it can unleash tremendous energy in the form of radiation and jets. This energy heats up the gas in the galaxy, making it too hot to collapse and form new stars. Think of it like blowing on a campfire. The flames might flicker and die down as the hot air disperses the fuel. In this way, black holes can put a lid on star formation, effectively pressing pause on a galaxy's growth. But here's the twist: black holes can also kickstart star birth under the right conditions. Those powerful jets and outflows we mentioned earlier don't just scatter gas. They can also slam into dense clouds, compressing them until they collapse under their own gravity. It's like squeezing a balloon until it pops, except instead of air, you get a burst of new stars. Some of the most intense star-forming regions in galaxies are found near these shockwaves, proving that black holes aren't just destroyers, they're also creators. The balance between these two roles depends on the black hole's activity and the galaxy's environment. In younger, gas-rich galaxies, black holes might trigger more star formation as their energy stirs up the cosmic soup. But in older galaxies, where gas is scarce, their heating effects can dominate, slowly shutting down star production over time. This delicate dance between creation and suppression helps explain why galaxies evolve so differently across the universe. And there's another layer to this story: feedback. Just like a thermostat regulates a room's temperature, black holes provide feedback to their galaxies, adjusting star formation rates to maintain equilibrium. Too many stars forming too quickly, the black hole ramps up its activity, heating the gas and slowing things down. Too quiet, its influence wanes, allowing cooler gas to accumulate and new stars to ignite. This self-regulating mechanism keeps galaxies from burning out too soon or growing unchecked. So whether they're lighting the spark or snuffing it out, black holes are master regulators of star formation, shaping the life cycle of galaxies in ways we're still unraveling. Next, we'll dive into the dazzling phenomena of quasars and active galactic nuclei, where black holes truly shine as the universe's most energetic powerhouses. Now, let's turn our attention to one of the most dazzling displays in the cosmos: quasars and active galactic nuclei. These are the universe's ultimate powerhouses, fueled by supermassive black holes in their most energetic states. Imagine a black hole so voracious that it devours entire stars and gas clouds, unleashing beams of light so intense they outshine entire galaxies. That's the raw power of a quasar. Quasars are actually a type of active galactic nucleus, or AGN for short, but they are the brightest and most extreme version. They form when a supermassive black hole at the center of a galaxy gorges itself on surrounding matter, heating it to unimaginable temperatures. As this material spirals inward, it glows fiercely, creating a brilliant disk of light that can be seen across billions of light years. In fact, The most distant quasars we've detected are like cosmic lighthouses, shining from a time when the universe was less than 1 billion years old. But quasars aren't just spectacular to observe. They played a crucial role in shaping the early universe. Their intense radiation and powerful jets acted like cosmic blowtorches, heating and ionizing the surrounding gas. This process helped clear the fog of the early cosmos, making space more transparent and allowing light to travel freely. Without quasars, the universe might have remained a murky, opaque place for much longer, delaying the formation of galaxies as we know them. Active galactic nuclei, though not as bright as quasars, still pack a punch. They come in different flavors, from Seyfert galaxies with their bright cores to radio galaxies that shoot out colossal jets of particles. What they all have in common is a supermassive black hole feeding on its surroundings, stirring up the galaxy in dramatic ways. Some AGN even flicker on and off over millions of years, depending on how much fuel is available. What's truly fascinating is how these energetic giants influenced galaxy evolution in the early universe. Their outbursts could trigger star formation in some regions while shutting it down in others, sculpting galaxies into the diverse shapes we see today. They also help distribute heavy elements forged in their fiery cores, seeding future generations of stars and planets. So while quasars and active galactic nuclei may seem like distant, exotic phenomena, they were key players in the cosmic story, shaping the universe from its infancy. Next, we'll explore how black holes grow even more massive through violent mergers, reshaping galaxies in the process. Now, picture this, a cosmic dance of unimaginable scale, where galaxies collide and their supermassive black holes spiral toward each other, locked in a gravitational embrace. This is where black hole mergers come into play, one of the most dramatic events in the universe. When two galaxies smash together, their central black holes eventually meet, creating a chaotic yet fascinating process that reshapes entire galactic structures. At first, the black holes orbit each other, slowly losing energy as they stir up nearby stars and gas. Over millions of years, their paths tighten until they finally merge in a cataclysmic event that sends ripples through space-time itself, gravitational waves. These waves, first detected in 2015, confirm just how violent and energetic these mergers can be. But the aftermath is just as important. The newly formed black hole is more massive, sometimes weighing in at hundreds of millions or even billions of times the mass of our sun. This growth isn't just about size, it's about influence. A larger black hole exerts an even stronger gravitational pull, altering the orbits of stars and gas clouds around it. In some cases, the merger can fling stars out of the galaxy entirely, while in others, it compresses gas clouds, sparking bursts of new star formation. The galaxy itself may transform, losing its spiral arms and settling into a smooth, elliptical shape. Interestingly, not all black hole mergers are equal. Some happen quickly, especially in dense galactic environments, where a third black hole can help kick the pair together. Others take much longer, lingering in a slow cosmic waltz before finally combining. And sometimes, the black holes don't merge at all. They stall, orbiting each other indefinitely in what astronomers call a binary system. What's truly remarkable is how these mergers tie into the larger story of galaxy evolution. Every time black holes collide, they leave a mark on their host galaxy, influencing its structure, star formation, and even its future collisions. Some of the most massive black holes we see today likely grew through multiple mergers, feasting on smaller ones over billions of years. So while black hole mergers might seem like rare, distant events, they're actually a key part of how galaxies grow and change over time. Next, we'll delve into an even deeper mystery: the possible connection between black holes and dark matter, and what that could mean for our understanding of the cosmos. Now, let's turn our attention to one of the most puzzling mysteries in the cosmos: the possible link between black holes and dark matter. While black holes are invisible because their gravity traps even light, dark matter is invisible because it doesn't interact with light at all. Yet, both hold immense gravitational influence over galaxies, shaping their evolution in ways we're still trying to understand. One intriguing theory suggests that some black holes, especially the smaller ones, could actually be made of dark matter. These so-called primordial black holes might have formed in the early universe from dense patches of dark matter collapsing under their own gravity. If they exist, they could explain part of the missing mass we attribute to dark matter today. Scientists are actively searching for signs of these elusive objects, watching for subtle distortions in starlight or ripples in space-time that might betray their presence. Another idea explores how dark matter behaves around black holes. Unlike ordinary matter, which heats up and emits light as it falls into a black hole, dark matter would simply pass through, unaffected. But its gravity could still shape the black hole's surroundings. Some models suggest dark matter might accumulate near black holes, creating dense halos that amplify their gravitational pull. This could explain why some supermassive black holes grow so massive so quickly. They might be feeding on dark matter as well as stars and gas. Then there's the question of whether black holes themselves could be producing dark matter. Certain theories propose that particles of dark matter might be created in the extreme environments near black holes, where gravity warps space and time to its limits. If true, this would mean black holes aren't just shaped by dark matter. They could be actively contributing to it, adding another layer to their role in galactic evolution. Of course, all of this remains speculative for now. Dark matter is famously difficult to study because it doesn't emit, absorb, or reflect light, leaving us to detect it indirectly through its gravitational effects. Black holes, while equally mysterious, at least reveal themselves by how they interact with visible matter. But as telescopes and detectors grow more advanced, we may soon uncover clues that bridge these two cosmic enigmas. What's clear is that the relationship between black holes and dark matter, if one exists, could reshape our understanding of how galaxies form and change over time. It's a reminder that the universe still holds secrets, waiting to be uncovered, secrets that might lie hidden in the darkness between the stars. Next, we'll explore how black holes might influence the very shape of galaxies, from their spiral arms to their smooth, elliptical forms. Now, let's take a closer look at how black holes might shape one of the most stunning features of galaxies: their elegant spiral arms. Picture the Milky Way, with its sweeping arms of stars, gas, and dust. swirling gracefully around a central core. What keeps these spirals intact? And could the supermassive black hole at the galaxy's heart play a role? One leading idea is that black holes act like cosmic anchors, their immense gravity helping to organize the motion of stars and gas clouds. As material orbits the black hole, it doesn't just move in random path. It can settle into patterns, like ripples in a pond. These patterns might reinforce the spiral structure, giving galaxies their iconic shape. Some simulations even suggest that without a central black hole, spiral arms could become loose or disordered over time, like a spinning top, losing its balance. But black holes don't work alone. Their gravitational pull interacts with another invisible force, dark matter. The dark matter halo surrounding a galaxy provides a kind of scaffolding, shaping how stars and gas move. Together, the black hole and dark matter create a delicate balance, one that keeps spiral arms tightly wound and stable for billions of years. It's a cosmic dance where gravity sets the rhythm and the black hole leads the way. There's also the question of star formation. Spiral arms are often dotted with bright, young stars, born from dense clouds of gas. Black holes might indirectly influence where and how these stars form. By stirring up the gas in the galaxy, either through their gravity or the energy released from their accretion disks, they could trigger pockets of star formation along the arms. In this way, black holes don't just shape the galaxy's structure, they might also light it up, one newborn star at a time. Yet mysteries remain. Not all spiral galaxies have equally active black holes, and some maintain their shape without obvious signs of black hole influence. This suggests that while black holes may play a key role, other factors, like collisions with smaller galaxies or the distribution of gas, could also contribute. The interplay is complex, and astronomers are still piecing together how all these forces work together. What's certain is that black holes are more than just destructive forces. They're architects, shaping the grand design of galaxies in ways we're only beginning to understand. Next, we'll explore how black holes leave their mark on a very different kind of galaxy, the smooth, featureless ellipticals, and how their influence can reshape entire cosmic neighborhoods. Now, let's turn our attention to a different kind of galactic masterpiece: elliptical galaxies. Unlike the swirling spirals we've just explored, ellipticals are smooth, round, and often devoid of the intricate arms that define their spiral cousins. But don't let their quiet appearance fool you. These galaxies have a dramatic story to tell, and at the heart of it lies their supermassive black hole. Elliptical galaxies are cosmic giants, packed with older stars and far less gas than spirals. This lack of gas means fewer new stars are born here, giving ellipticals their calm, uniform glow. But how did they end up this way? One key player is the black hole's feedback mechanism, a process where the black hole's activity heats up or even ejects gas from the galaxy. Imagine the black hole as a cosmic thermostat. When it feeds on surrounding material, it doesn't just swallow everything quietly. Instead, it releases tremendous energy in the form of jets or winds, like a furnace blasting heat. This energy can heat the galaxy's remaining gas to such high temperatures that it can't cool down and form new stars. In some cases, The black hole's outbursts are so powerful, they push gas entirely out of the galaxy, starving it of the raw material needed for future star formation. This feedback process is like a balancing act. If the black hole grows too active, it can shut down star formation completely, leaving the galaxy to age gracefully with its existing stars. But if the black hole is too quiet, gas might accumulate, leading to bursts of star formation that could disrupt the galaxy's smooth structure. It's this delicate interplay that helps maintain the elliptical galaxy's signature look, a serene, star-filled orb with little drama on the surface, but a turbulent history beneath. Interestingly, this feedback doesn't just affect the galaxy itself, it can reshape its entire surroundings. The gas expelled by the black hole might mix with the wider intergalactic medium, enriching it with heavy elements and influencing the growth of neighboring galaxies. In this way, the black hole's reach extends far beyond its home galaxy, leaving a mark on the cosmic neighborhood. Of course, not all elliptical galaxies follow the same script. Some show signs of past collisions or mergers, which can stir up gas and reignite black hole activity. Others might have quieter black holes, their feedback mechanisms less extreme. But one thing is clear, black holes are master regulators, shaping not just the fate of their host galaxies, but the broader tapestry of the universe. Next, we'll venture into the realm of dwarf galaxies, where black holes play by a different set of rules, or sometimes don't seem to play at all. What secrets do these tiny cosmic islands hold, and how do their black holes compare to the giants we've seen so far? Now, let's shift our gaze to the smaller, often overlooked members of the cosmic family, dwarf galaxies. These tiny islands of stars, gas, and dust may lack the grandeur of their spiral or elliptical cousins, but they hold fascinating clues about how black holes behave on a smaller scale. Unlike the supermassive giants at the heart of larger galaxies, black holes in dwarf galaxies, when they exist at all, play by a different set of rules, offering a unique window into galactic evolution. Dwarf galaxies are the underdogs of the universe, typically containing only a fraction of the stars found in galaxies like the Milky Way. Many of them are so small and faint, they'd easily get lost in the glow of a single bright star from a larger galaxy. Yet, despite their modest size, they're incredibly important. Some dwarf galaxies host black holes, but these are far less massive than the supermassive ones we've discussed so far. Others seem to lack black holes entirely, raising questions about why some galaxies get them and others don't. When a dwarf galaxy does have a black hole, it's usually what astronomers call an intermediate mass black hole, bigger than the stellar mass black holes left behind by collapsing stars, but nowhere near the size of a supermassive one. These middleweight black holes are intriguing because they might represent an early stage in the growth of their supermassive cousins. Imagine them as cosmic seeds, slowly gathering mass over time through mergers or by pulling in surrounding gas. But here's where things get interesting. Unlike supermassive black holes, which often dominate their galaxies with powerful feedback, dwarf galaxy black holes tend to have a much quieter influence. Their gravitational pull isn't strong enough to dramatically reshape their surroundings, and their energy output is far more subdued. This means they don't typically shut down star formation or blow gas out of their galaxies like their larger counterparts do. Instead, they might gently nudge their host galaxies' evolution, subtly affecting how stars form and move over billions of years. Some dwarf galaxies, however, defy expectations entirely. A rare few have been found with surprisingly active black holes, emitting bright X-rays or even producing small jets. These outliers challenge our understanding of how black holes and galaxies grow together. Could these active dwarfs be the remnants of larger galaxies stripped down by collisions, or are they evidence that black holes can form and grow in unexpected ways? These questions keep astronomers digging deeper into the mysteries of these tiny cosmic systems. Then there are the many dwarf galaxies that show no signs of hosting a black hole at all. This absence is just as telling as their presence. It suggests that not every galaxy, no matter how small, necessarily forms or retains a central black hole. Some might have lost theirs during violent encounters with larger galaxies, while others may have never had one to begin with. Studying these black hole-free dwarfs helps scientists piece together the conditions needed for black holes to take root and thrive. What's clear is that dwarf galaxies, with or without black holes, are vital pieces of the cosmic puzzle. They remind us that black holes don't always follow the same script, and their role in galactic evolution can vary dramatically depending on the size and history of their host. By studying these miniature galaxies, we gain a fuller picture of how black holes shape the universe, from the mightiest ellipticals to the humblest dwarfs. Next, we'll explore another way black holes leave their mark on galaxies, through the powerful winds they generate, capable of sweeping gas across vast cosmic distances. How do these galactic gusts alter the destiny of the galaxies they blow through? Now, let's turn our attention to one of the most dramatic ways black holes shape their galaxies, through the colossal winds they unleash. Picture a cosmic storm, fierce enough to sweep entire clouds of gas out of a galaxy, altering its destiny forever. These aren't ordinary breezes but supersonic gusts, powered by the incredible energy of active black holes at the hearts of galaxies. When a supermassive black hole feeds on surrounding material, it doesn't just swallow gas and dust quietly. Some of that material gets superheated and blasted outward at nearly the speed of light, creating vast streams of charged particles. These outflows can stretch for thousands of light years, carrying enough energy to push gas, the very fuel for new stars, right out of the galaxy. It's like a cosmic gardener pruning a tree, but on a scale so immense it can stunt a galaxy's growth for billions of years. The impact of these winds is profound. In some galaxies, they blow so fiercely that they clear out entire regions of star-forming gas, effectively putting a halt to new star birth. Without fresh generations of stars, these galaxies age prematurely, their populations of stars growing older and redder over time. This might explain why some galaxies, especially massive ellipticals, are filled with ancient stars and very little gas. Their black holes blew away the raw materials needed for new ones. But galactic winds aren't just destructive. In a surprising twist, they can also be creative forces. By sweeping gas outward, they sometimes compress it in other regions, triggering bursts of star formation in their wake. Imagine a gust of wind piling leaves into a corner, except here, the leaves are giant clouds of gas, and the corner might be a distant spiral arm or even a neighboring galaxy. This duality makes black hole winds both architects and wreckers, shaping galaxies in ways we're still unraveling. The sheer power of these outflows is staggering. Some winds reach temperatures of millions of degrees, glowing brightly in X-rays as they race through space. Others carry magnetic fields strong enough to influence gas far beyond their host galaxy, weaving a web of influence that stretches across cosmic distances. These winds don't just alter their own galaxies, they can affect entire clusters of galaxies, redistributing matter on scales almost too vast to comprehend. Yet, not all black hole winds are the same. Some are narrow, focused jets, drilling through space like cosmic lasers. Others are broad, chaotic outflows, more like a hurricane than a beam. The difference depends on the black hole's appetite, the angle at which we observe it, and the environment around it. Studying these variations helps astronomers piece together how black holes and their host galaxies co-evolve, each shaping the other over billions of years. What's truly remarkable is how these winds connect the smallest and largest scales of the universe. A process that begins near a black hole's event horizon can dictate the fate of a galaxy 100,000 light-years away. It's a reminder of how interconnected the cosmos is, with black holes acting as both anchors and agitators in the grand story of galactic life. Next, we'll delve into another invisible force shaping this cosmic dance: the magnetic fields that twist and turn around black holes, guiding their powerful outbursts and sculpting the space around them. How do these unseen lines of force shape the chaos they touch? Now, let's pull back the curtain on another invisible player in this cosmic drama: the magnetic fields that wrap around black holes like unseen puppet strings. These fields might not glow like accretion disks or blast matter outward like jets, but they're quietly directing the chaos, shaping how black holes interact with their galactic surroundings. Picture a black hole's magnetic field as a cosmic spiderweb, stretching far beyond the event horizon. As matter spirals inward, it doesn't just fall in smoothly. It gets tangled in these magnetic lines, which twist and snap like rubber bands under unimaginable pressure. When they break, they release bursts of energy that can accelerate particles to nearly the speed of light. This is why some black holes shoot out those narrow, focused jets we see piercing through galaxies. The magnetic fields act like cosmic railguns, channeling the chaos into precise, high-speed beams, but their influence doesn't stop there. Magnetic fields also help control how a black hole feeds. Think of them as bouncers at a cosmic nightclub, deciding which gas clouds get sucked in and which get flung away. They can stir the accretion disk into turbulent whirlpools, creating hotspots that glow brighter in X-rays. This turbulence even affects how much material ultimately crosses the event horizon, meaning magnetic fields indirectly dictate how hungry or quiet a black hole becomes over time. On a galactic scale, these fields weave through the winds and jets we discussed earlier, giving them structure. Without magnetic fields, outflows would be shapeless blobs of gas. Instead, they're sculpted into narrow streams or wide fans, depending on how the fields twist and fold. Some astronomers compare it to the way Earth's magnetic field shapes the auroras, except here, the light show spans thousands of light years, and the northern lights are made of superheated plasma. Perhaps most intriguing is how magnetic fields might solve a cosmic mystery. Why some black holes seem to flicker like faulty light bulbs. Rapid changes in brightness, sometimes in just hours, could stem from magnetic reconnection events. That's when field lines break and reconnect, releasing energy in sudden bursts. It's the same process that powers solar flares on our sun, but around a black hole, the scale is mind-bending. A single reconnection could unleash enough energy to power a star for millennia. Yet, for all their power, magnetic fields around black holes remain elusive. They don't emit light directly, so astronomers have to study them indirectly, by observing how they bend jets, polarize light, or influence the motion of nearby particles. It's like trying to map a maze by watching how the wind blows through it. But each clue helps us understand how these invisible forces shape galaxies, from the tiniest eddies near the event horizon to the vast outflows that redefine entire galactic neighborhoods. Next, we'll venture into one of the most mind-bending consequences of black holes, the way they warp time itself. How does time dilation near these cosmic monsters alter our understanding of galactic evolution? Now, let's step into one of the most bewildering realms of black hole physics, where time itself bends to their will. Near a black hole, gravity is so intense that it doesn't just warp space. It stretches time like taffy, creating a phenomenon called time dilation. Imagine two astronauts. One orbits dangerously close to the event horizon, while the other watches from a safe distance. For the distant observer, time for their brave companion slows to a crawl. Minutes for the orbiting astronaut could stretch into years for the observer. This isn't science fiction. It's Einstein's theory of relativity in action, revealing how black holes twist the very fabric of reality. But how does this surreal time warp affect galaxies? Picture a supermassive black hole at a galaxy's core, where time passes far slower than in the outer regions. This means processes near the center like gas accretion or star formation unfold at a different pace compared to the galaxy's outskirts. Over millions of years, this time gradient could create a kind of cosmic traffic jam, with material piling up near the center while the outer regions evolve more freely. Some scientists speculate that this might explain why galactic cores often appear older or more evolved than their surrounding disks. Time dilation also plays a role in the energetic outbursts from active black holes. When jets or winds are launched near the event horizon, their light takes longer to escape the intense gravity, making flares or bursts appear to last longer from our distant vantage point. This time-stretching effect could disguise how quickly black holes actually influence their surroundings, tricking us into thinking certain events unfold gradually when, near the black hole, they're happening in a blink. Even more intriguing is how time dilation might affect the black hole's own evolution. From our perspective, a black hole's life appears to slow as it grows denser, almost as if it's aging in slow motion. This could mean that the most massive black holes we observe are, in their own frame of reference, evolving far faster than we can detect. It's a paradox that challenges how we measure cosmic timelines and understand the growth of these galactic giants. While time dilation near black holes might seem like an abstract curiosity, its ripple effects could shape entire galaxies. By warping time, black holes may subtly orchestrate the pace of star formation, the flow of gas, and even the way galaxies collide and merge. It's a reminder that in the cosmic dance of evolution, black holes don't just move to the music, they control the tempo. Next, we'll explore how black holes act as cosmic recyclers, devouring stars only to seed new ones with the material they fling back into space. Now, let's shift our gaze to one of the most fascinating roles black holes play in the universe: cosmic recycling. Far from being mere destroyers, these gravitational giants are also creators, shaping the life cycle of matter in ways that keep galaxies vibrant and evolving. When a black hole pulls in a star or a cloud of gas, it doesn't just vanish forever. Some of that material spirals into an accretion disk, superheated to incredible temperatures before plunging beyond the event horizon. But not everything gets swallowed. Powerful magnetic fields and intense radiation can fling some of that matter back into space at nearly the speed of light. These outflows, whether as jets or winds, carry heavy elements forged in the hearts of stars: carbon, oxygen, iron, and scatter them across the galaxy. This process is like a cosmic sprinkler system, seeding the surrounding space with the raw ingredients for new stars and planets. In fact, some of the atoms in your body might have once been part of a star that fell into a black hole, only to be hurled back out and recycled into the universe. Without this constant churn of matter, galaxies would eventually run out of the building blocks needed for new generations of stars. But black holes don't just recycle material, they also regulate how it's distributed. The energy from their jets and winds can push gas outward, preventing it from collapsing into stars too quickly. In some cases, this slows down star formation, keeping galaxies from burning through their fuel too fast. In others, the shock waves from these outflows compress nearby gas clouds, triggering bursts of new star birth. It's a delicate balance, with black holes acting as both brakes and accelerators in the life cycle of galaxies. Even more remarkable is how these recycled elements can travel vast distances. A single black hole eruption can send material shooting hundreds of thousands of light years away, enriching far-off regions of a galaxy or even neighboring galaxies. Over billions of years, this cosmic redistribution ensures that no corner of the universe is left untouched by the cycle of creation and destruction. So while black holes might seem like the ultimate endpoints for matter, they're also key players in its renewal. They take what was old and spent, transform it, and send it back out to begin anew. It's a reminder that in the grand story of the cosmos, nothing is truly lost, only reshaped. Next, we'll delve into the dramatic process of galactic cannibalism, where black holes play a starring role in the collisions and mergers that reshape entire galaxies. Now, let's turn our attention to one of the most dramatic events in the cosmos: galactic cannibalism. Picture this: a massive galaxy drifting through space, slowly pulling a smaller neighbor into its gravitational grip. Over millions of years, the smaller galaxy is torn apart, its stars and gas absorbed into the larger one, and at the heart of this cosmic feast, a supermassive black hole orchestrating the entire collision. These mergers aren't just random acts of destruction. They're a fundamental part of how galaxies grow and evolve. When two galaxies collide, their central black holes eventually spiral toward each other, locked in a gravitational dance. As they draw closer, they stir up the surrounding gas and stars, creating chaotic swirls of material. The energy released can trigger bursts of star formation, or even fling stars out into intergalactic space. But the real spectacle happens when the black holes finally merge. The impact sends ripples through space-time itself, gravitational waves that astronomers can now detect. These collisions are so powerful, they can kick the newly formed black hole out of the galaxy's center, sending it hurtling through space. Yet even then, its influence lingers. The merged black hole grows even more massive, shaping its host galaxy's future by controlling how stars form and where gas accumulates. What's fascinating is how these events recycle entire galaxies. The smaller galaxy's stars don't just disappear, they become part of the larger galaxy's structure, often forming streams or shells of stars that trace the merger's history. Meanwhile, the influx of fresh gas can reignite star formation, giving the cannibal galaxy a new lease on life. Our own Milky Way is no stranger to this process. It's thought to have devoured dozens of smaller galaxies over its lifetime, with each merger leaving behind clues in the form of star clusters or distorted orbits. And in the distant future, it's destined to collide with the Andromeda Galaxy, a merger that will reshape both in ways we can only imagine. So while the term cannibalism might sound violent, these mergers are really about transformation. Black holes don't just destroy, they rebuild, weaving smaller galaxies into larger tapestries and ensuring the universe remains a dynamic, ever-changing place. Next, we'll take a closer look at the Milky Way's own supermassive black hole, Sagittarius, a star, and how it quietly shapes our cosmic neighborhood. Now, let's zoom in on our own cosmic backyard and meet the quiet giant at the heart of the Milky Way, Sagittarius, a star. This supermassive black hole, though invisible to the naked eye, has been shaping our galaxy's destiny for billions of years. Discovered not by sight, but by tracking the wild orbits of nearby stars, Sagittarius, a star, revealed itself through its immense gravitational pull. Astronomers watched as these stars whipped around an unseen point at breathtaking speeds, some completing their orbits in just a few decades. The math was undeniable. Something with the mass of 4 million suns had to be lurking there, hidden in the darkness. What's surprising is how calm Sagittarius, a star, appears compared to other supermassive black holes. While some devour gas and dust in spectacular displays, ours is more of a quiet neighbor, only occasionally flaring up as it snacks on passing material. But don't let its subdued nature fool you. Its gravity still dictates the motion of stars across our galaxy, weaving them into the spiral arms we see today. Even at its distance, 27,000 light-years from Earth, Sagittarius, a star's influence is undeniable. It acts like an anchor, stabilizing the Milky Way's structure while subtly steering the flow of gas and dust. Without it, our galaxy might look very different, possibly losing its distinctive spiral shape over time. Yet there's still so much we don't understand. Why is it so quiet compared to other supermassive black holes? What triggers its occasional outbursts? And how did it grow to such an enormous size in the first place? These mysteries keep astronomers glued to their telescopes, watching every flicker and flare for clues. One thing's certain: Sagittarius, a star, isn't done shaping our galaxy. In the distant future, when the Milky Way collides with Andromeda, this black hole will play a starring role, merging with its counterpart to create an even more massive cosmic engine. Until then, it remains our silent guardian, quietly holding the Milky Way together. Next, we'll explore an intriguing question. Could black holes actually affect the potential for life in galaxies, or do they create conditions too extreme for life to thrive? Now, let's turn our gaze to a fascinating question. Could black holes actually play a role in making galaxies habitable, or do they create conditions too extreme for life to exist? At first glance, these cosmic behemoths seem like the ultimate destroyers, but their influence might be more nuanced than we think. Take the supermassive black hole at the center of a galaxy, like our own Sagittarius, a star. While its intense gravity and radiation might seem like a threat, it could also be a stabilizing force. By anchoring the galaxy's structure, it helps maintain orderly orbits for stars and planetary systems. Without that central pull, galaxies might become chaotic, with stars flung into unpredictable paths, hardly a stable environment for life to emerge. But there's a flip side. Active black holes, especially those devouring large amounts of matter, unleash powerful jets of radiation and particle winds. These can sterilize entire regions of a galaxy, stripping away atmospheres or preventing planets from forming in the first place. Imagine a cosmic hurricane sweeping through, leaving little chance for life to take hold. Yet, paradoxically, these same violent outbursts might also trigger star formation in distant gas clouds, creating new cradles for potential life. Then there's the Goldilocks zone, not just around stars, but around black holes themselves. At just the right distance, a planet might benefit from the heat of an accretion disk without being fried by radiation. It's a wild idea, but some theories suggest that under very specific conditions, life could exist in these extreme environments, perhaps even harnessing the black hole's energy. Of course, we're still piecing together the puzzle. Could the quiet nature of black holes like Sagittarius, a star, actually make galaxies more life-friendly by avoiding catastrophic outbursts? Or do even dormant black holes subtly influence habitability through their gravitational whispers? The answers might reshape how we search for life beyond Earth, pointing us toward galaxies where black holes strike the perfect balance between chaos and calm. Next, we'll journey back to the dawn of the universe, where mysterious primordial black holes might have shaped the very first galaxies in ways we're only beginning to understand. Now, let's rewind the cosmic clock to a time when the universe was just a newborn, buzzing with energy and mystery. Among the earliest inhabitants of this ancient cosmos might have been primordial black holes, tiny, dense, and unlike anything we see today. These aren't the black holes born from collapsing stars. Instead, they could have formed in the first chaotic moments after the Big Bang, when extreme pressures and temperatures squeezed matter into microscopic knots of gravity. Imagine the universe as a bubbling soup of particles, so hot and dense that random fluctuations could have created pockets of space so warped they collapsed into black holes. Some might have been as small as an atom, yet packed with the mass of a mountain. Others could have rivaled the heft of entire stars. Unlike their modern counterparts, these primordial black holes wouldn't need a star's death to exist. They were there from the very beginning, lurking in the shadows of the infant cosmos. What makes them so intriguing is their potential role as cosmic seeds. In the early universe, matter was spread thinly, but a primordial black hole could have acted like a gravitational anchor, pulling gas and dust toward it. Over eons, these gatherings might have grown into the first protogalaxies, the building blocks of the majestic spirals and ellipticals we see today. Some scientists even speculate that these ancient black holes could be the hidden roots of today's supermassive giants, having feasted and merged their way to enormous sizes over billions of years. But here's the twist. If primordial black holes were abundant, they might also have shaped the universe in ways we're only starting to uncover. Their gravity could have influenced the distribution of dark matter, or even triggered the formation of the first stars earlier than expected. And because they'd be nearly invisible, too small to emit detectable radiation, they might still be out there, drifting unseen through galaxies, including our own. The hunt for these elusive relics is ongoing. Astronomers scour the cosmos for subtle clues, like unexpected gravitational lensing or strange bursts of radiation that might betray their presence. Finding one would be like uncovering a fossil from the universe's first moments, offering a glimpse into a time when everything was just taking shape. As we peel back the layers of this cosmic mystery, we're reminded that black holes aren't just destroyers. They might have been among the universe's first architects, quietly shaping the galaxies we call home. Next, we'll step into the cutting-edge world of black hole imaging, where science and technology unite to reveal the unseeable. Now, let's shift our gaze to one of the most astonishing breakthroughs in modern astronomy, the first ever image of a black hole shadow. Picture this, a dark void encircled by a fiery ring of light, a snapshot of the unimaginable. This historic moment wasn't just a triumph of technology, it was a window into the heart of darkness itself. The black hole in question lies at the center of the galaxy Messier 87, 55 million light-years away. Capturing its shadow required a telescope as wide as Earth itself, the Event Horizon Telescope, a global network of observatories working in perfect harmony. The result, a blurry but unmistakable image of a black hole silhouette, its event horizon bending light into a glowing halo. What does this reveal? For starters, it confirmed Einstein's century-old predictions about how gravity warps space and time. The shadow's size and shape matched his equations with uncanny precision, proving that black holes aren't just theoretical oddities, they're real, and they behave exactly as relativity foretold. But the image also offered clues about how black holes interact with their galaxies. The swirling light around the shadow comes from superheated gas spiraling inward, a process that fuels the black hole's growth and in turn shapes its galactic home. This breakthrough didn't just satisfy scientific curiosity, It opened new doors. By studying these shadows, astronomers can now measure black holes' spins, map their magnetic fields, and even test alternative theories of gravity. Each new image adds another piece to the puzzle, helping us understand how these cosmic titans influence everything from star formation to galactic collisions. And the best part, this is only the beginning. Future telescopes will capture sharper images, perhaps even revealing the shadow of Sagittarius, a star, the supermassive black hole at the Milky Way's heart. With every glimpse into these dark giants, we're not just seeing black holes, we're seeing the invisible hands that sculpt our universe. Next, we'll peer into the distant future, where black holes continue to shape galaxies in ways we're only starting to imagine. Now, let's journey forward in time, far beyond our own era, to explore how black holes will continue to shape the cosmos in the distant future. Imagine a universe where galaxies have grown older, their stars dimmer, and their black holes even more dominant. Over billions of years, these gravitational giants will play a starring role in the fate of their galactic homes. As galaxies collide and merge, their central black holes will spiral toward each other, eventually merging as well. These cosmic crashes send ripples through spacetime, gravitational waves that echo across the universe. With each merger, the resulting black hole grows larger, its gravitational pull tightening its grip on the surrounding stars and gas. Over time, this process could lead to the formation of unimaginably massive black holes, some weighing in at hundreds of billions of times the mass of our Sun. But what happens when the universe grows even older? Stars will burn out, and new ones will stop forming as galaxies run out of gas. Without fresh material to feed on, black holes will slowly starve, their accretion disks fading into darkness. Yet even in this quiet era, black holes won't disappear. They'll linger, their immense gravity still bending the paths of any remaining stars or wandering planets. In the far, far future, trillions of years from now, black holes might be the last significant objects left in the universe. As space continues to expand, galaxies will drift apart, leaving isolated supermassive black holes floating in an ever-cooling cosmos. Eventually, even these titans will meet their end, evaporating over incomprehensible timescales through a process called Hawking radiation. But that's a story for another era. For now, black holes remain the architects of galactic evolution, shaping the universe in ways both visible and invisible. Their influence stretches across time, from the birth of galaxies to their distant, quiet demise. And as we continue to study them, we uncover not just the fate of galaxies, but the ultimate story of the cosmos itself. Next, we'll step into the realm of science fiction, where black holes have captured our imagination in ways both thrilling and wildly speculative. Now, let's take a playful detour from the science and step into the world of imagination, where black holes have long been a favorite playground for storytellers. In movies, books, and TV shows, black holes often take on dramatic roles: portals to other dimensions, time machines, or even cosmic monsters lurking in the shadows of space. Think of films like Interstellar, where a black hole becomes a gateway to humanity's salvation, bending time and space in ways that dazzle the mind. Or consider the terrifying depiction in Event Horizon, where a black hole is twisted into a nightmare realm of pure chaos. But how do these fictional portrayals stack up against reality? While black holes are undeniably strange and powerful, they don't quite behave like the Hollywood versions. Real black holes don't whisk travelers to alternate universes or spew out ghostly horrors. Instead, their true nature is just as fascinating, if not more so. The extreme gravity near a black hole's event horizon does warp time, but not in a way that lets us hop through eras like a time-traveling adventurer. And while their pull is inescapable, they don't actively suck in distant objects like a cosmic vacuum cleaner. Matter has to stray dangerously close to get caught. Science fiction also loves to exaggerate the visual spectacle of black holes, often showing them as swirling, glowing vortexes. In reality, a black hole itself is invisible. What we see in images like the famous first photo of M87's black hole is the glowing gas and light trapped in its accretion disk, not the hole itself. Even the eerie silence of space is a far cry from the rumbling, ominous soundtracks that accompany black holes on screen. Yet, for all their creative liberties, these stories do something important. They spark curiosity. They get people asking questions, wondering what's really out there, and sometimes the wildest ideas in fiction inspire real scientists to explore new theories. After all, the line between science and science fiction has always been blurry, with discoveries often proving stranger than anything we could dream up. So while black holes may not be the cosmic shortcuts or haunted gateways of our stories, they remain one of the universe's most thrilling mysteries, both in science and in our imaginations. Next, we'll turn to the unanswered questions that still puzzle astronomers, diving into the biggest mysteries surrounding black holes and their role in shaping galaxies. Even as we uncover more about black holes and their cosmic influence, some of the most fascinating questions remain wide open, teasing scientists with their mysteries. One of the biggest puzzles is how supermassive black holes grew so enormous so quickly in the early universe. Some of these giants existed when the cosmos was less than 1 billion years old, leaving astronomers scratching their heads over how they had enough time to form. Were they born large, or did they devour matter at unimaginable rates? Theories range from colossal collapsing gas clouds to chains of merging smaller black holes, but the truth is still out there. Then there's the enigma of what exactly happens inside a black hole. We know matter gets crushed into an infinitely dense point, called a singularity, but our laws of physics break down there. Does something strange happen to space and time at the center? Could there be a doorway to another universe, as some wild but unproven theories suggest? Without a way to peek inside, these questions push the limits of both science and imagination. Another head-scratcher is the relationship between black holes and dark matter. Could dark matter, the invisible stuff making up most of the universe's mass, somehow feed black holes, or even be connected to their formation? Some scientists wonder if tiny primordial black holes, forged in the chaos of the Big Bang, might actually be dark matter. It's a tantalizing idea, but so far, the evidence is elusive. Even the way black holes shape galaxies isn't fully understood. We know they influence star formation, and galactic structure, but the details are messy. Why do some black holes blast out jets that heat up entire galaxies, while others sit quietly? How do they communicate with their surroundings to create such precise balances? Every new discovery seems to add another layer of complexity. And let's not forget the biggest question of all: what's the ultimate fate of a black hole? Stephen Hawking theorized they slowly evaporate over eons, but no one's ever observed it happening. If they do vanish, what happens to all the information they swallowed? The debate rages on, with experiments and telescopes hunting for clues. What's exciting is that these aren't just abstract riddles. Teams around the world are racing to solve them, using everything from gravitational wave detectors to supercomputer simulations. Every year, we get a little closer to answers, and who knows, the next breakthrough might rewrite our understanding of the cosmos. Now, let's shift our gaze to the tools and techniques astronomers use to study these cosmic enigmas, from radio telescopes to space-based observatories. Peering into the cosmic shadows where black holes lurk requires more than just ordinary telescopes. Scientists have assembled an impressive toolkit to study these invisible giants, each method revealing a different piece of the puzzle. Radio telescopes, for instance, capture the faint whispers of matter swirling around black holes, painting vivid images of their surroundings. The Event Horizon Telescope, a global network of radio dishes, made history by snapping the first ever picture of a black hole's shadow, a glowing ring of light bending around the abyss. But sometimes, black holes announce their presence through violent motions rather than light. Gravitational wave detectors like LIGO and Virgo sense ripples in spacetime itself, created when black holes collide. These cosmic tremors allow us to hear mergers that happened billions of years ago, revealing black holes we'd never see otherwise. Meanwhile, X-ray telescopes in space, like Chandra, focus on the superheated gas in accretion disks, where temperatures soar to millions of degrees. By analyzing these high-energy fingerprints, astronomers can measure a black hole's spin and even track how it devours nearby stars. Infrared observatories, such as the James Webb Space Telescope, peer through cosmic dust to study how black holes influence their galaxies. They've caught black holes in the act of flinging out winds so powerful they can halt star formation across entire galaxies. And then there are neutrino detectors, which hunt for ghostly particles spat out during the most violent black hole activity. Each tool acts like a different sense, helping us piece together a fuller picture of these enigmatic objects. What's truly remarkable is how astronomers combine these techniques. A single black hole might be observed through gravitational waves, X-rays, and radio waves simultaneously, offering a multidimensional view of its behavior. As technology advances, so does our ability to probe deeper into the mysteries of black holes, bringing us closer than ever to understanding their role in shaping the universe. Now, let's step into the digital realm, where supercomputers simulate black hole encounters too extreme for telescopes to witness firsthand. To unlock the secrets of black holes beyond what telescopes can show, scientists turn to the digital universe. Inside powerful supercomputers, they recreate cosmic conditions too extreme to observe directly, simulating how black holes behave and shape their surroundings. These virtual experiments allow us to witness collisions between supermassive black holes, watch galaxies merge, and see how black holes launch jets of particles at nearly the speed of light, all from the safety of a computer screen. The process starts with equations from Einstein's theory of relativity, which describe how black holes warp space and time. Researchers feed these rules into simulations, along with data from real observations, to build accurate digital models. Some simulations focus on the chaotic dance of stars and gas around a single black hole, revealing how its gravity stirs the galactic center like a cosmic whirlpool. Others track the fate of entire galaxies when their central black holes awaken, blasting out energy that can heat or expel gas across thousands of light years. One of the most dramatic simulations shows what happens when two galaxies collide, forcing their supermassive black holes to spiral toward each other. As they draw closer, they warp spacetime so violently that they emit gravitational waves ripples that future observatories might detect. Some models even suggest that these mergers can kick the resulting black hole out of its galaxy entirely, sending it wandering through the cosmos. But simulations aren't just about spectacle. They help solve real mysteries, like why some galaxies stop forming stars, or how black holes grow so quickly in the early universe. By comparing virtual results with telescope data, scientists refine their theories, uncovering new clues about how black holes and galaxies evolve together. Every simulation is a test, pushing our understanding to the limits, and sometimes revealing surprises that send researchers back to the drawing board. As computing power grows, so does the detail in these virtual experiments. Soon, simulations may even bridge the gap between the tiny scale of black holes and the vast structure of the cosmos, showing how these invisible giants sculpt the universe on the grandest scales. Now, let's venture into one of the most mind-bending ideas in modern physics, the possibility that black holes might be gateways to other universes. While this sounds like science fiction, some theories in physics actually leave the door open for such extraordinary possibilities. At the heart of these ideas is the concept that black holes don't just trap matter and light, they might also warp the fabric of reality itself. One intriguing theory suggests that the singularity at the center of a black hole, the point where gravity becomes infinitely strong, could be a bridge to another universe. This idea comes from solutions to Einstein's equations of relativity, which show that a black hole's singularity might connect to a white hole in another region of spacetime. A white hole would be the opposite of a black hole, spewing out matter and energy instead of swallowing it. Some scientists speculate that this could form a tunnel or wormhole between two separate universes. Of course, there's no direct evidence for this yet, and the math behind it is highly speculative. The extreme conditions near a black hole's singularity push our current understanding of physics to its limits. Quantum mechanics and general relativity, our best theories for the very small and the very massive, clash violently in this realm. Until we have a theory of quantum gravity to bridge the gap, these ideas remain fascinating but unproven possibilities. Another wild hypothesis ties black holes to the multiverse. The idea that our universe is just one of countless others, each with its own laws of physics. Some theories propose that new universes could be born inside black holes, with their own expanding spacetime. If true, this would mean every black hole in our cosmos might contain an entire universe within it. While these theories stretch the imagination, they're not pure fantasy. They emerge from serious attempts to solve deep puzzles in physics, like the fate of information that falls into a black hole or the nature of the Big Bang itself. Experiments to test these ideas are far off, but future advances in gravitational wave astronomy or quantum physics might one day offer clues. For now, the multiverse and black holes remain a thrilling frontier where science and speculation meet. Whether they're cosmic gateways or just incredibly dense objects, black holes continue to challenge our understanding of reality, and that's what makes them so endlessly fascinating. As we bring our cosmic journey to a close, let's take a moment to reflect on the incredible role black holes play in shaping the universe around us. From their violent births in the collapse of massive stars to their quiet dominance at the centers of galaxies, these mysterious objects are far more than cosmic vacuum cleaners. They are architects of galactic evolution, sculpting the paths of stars, regulating star formation, and even powering some of the brightest phenomena in the cosmos. Think of black holes as the invisible hands guiding the fate of galaxies. Their immense gravity dictates the motion of stars and gas, while their explosive outbursts can ignite new stars or blow away the raw materials needed to make them. They are both creators and destroyers, weaving a delicate balance that shapes the galaxies we see today. And as galaxies collide and merge, their black holes often unite, growing ever larger and reshaping their cosmic neighborhoods in the process. Yet for all their power, black holes remain shrouded in mystery. We've only begun to unravel their secrets, from the first stunning image of a black hole's shadow to the detection of gravitational waves from their collisions. Each discovery peels back another layer, revealing just how deeply these enigmatic objects are woven into the fabric of the universe. So as you drift into sleep tonight, let your mind wander among the stars. Picture the swirling dance of galaxies, each one cradling a black hole at its heart. Imagine the vast cosmic web they help shape and the countless worlds that might orbit under their influence. In this grand tapestry of space and time, we are but fleeting observers, humbled by the beauty and complexity of it all. Thank you for joining me on this journey through the cosmos. If you enjoyed exploring the mysteries of black holes and galaxies, don't forget to like this video, subscribe for more cosmic stories, and hit the notification bell so you never miss an adventure. Sweet dreams, and may your thoughts be as boundless as the universe itself. you.